Hello everyone, welcome to Lab 2 Experiments. This is Machine Health Monitoring section, and today we'll perform experiment number 3, which is Introduction to Vibrations. So in general, what is vibration? Vibration is the study of oscillatory motions of bodies and forces associated with them. In general, all physical bodies and structures, they possess mass and stiffness, and they are capable of exhibiting vibrations. In some cases, in engineering cases, vibration plays an important role. In others, it's negligible. So it's up to the vibration analysis so that we can decide which case it will affect our system and which case will not. And today in this experiment, we'll explore three topics. The first one is vibration fundamentals in general. The second is the case of undamped vibration. And third topic is damped vibration. So we will have a fundamentals and then two types, undamped and damped vibrations. So the first section is 3.1, the fundamentals of vibration. In this experiment, the objective is to introduce the fundamental vibrations, terms like vibration, displacement, which is amplitude, velocity, frequency, and acceleration. So the basic concepts of vibration analysis. And we define the spring mass model, equation, and harmonic motion of that system, and the harmonic motion of that system. So the spring mass model, so if we look at this picture, we have the spring attached to a mass, and then if we assume that we have some displacement, initial displacement, if we take this mass down, after a while it will start oscillating. It will go up and down, up and down, up and down. Why? Because the energy is stored in the spring. So this system has an inertia, which is mass, and also it has a stiffness, which is spring. So because of these two elements, the system will start vibrating or oscillating, and this is the definition of vibration. So the spring mass model, we can define the force in the spring with the formula F equal Kx. Of course, this is case of linear spring. So K is the stiffness of the spring, F is the force, and X is the displacement of the spring. And the same thing, if we have some damping element C, the damping element C will cause that motion to die or reduce the motion of the vibration or the oscillation. The force of damping will be equal to the damping coefficient C multiplied by the velocity x dot. So two things, two forces. The force of the elastic element or the spring will be linearly related to the x, which is displacement. The force of damping element will be related to the velocity x dot. So how to find the harmonic motion, or how to expect or predict the motion of that system? So we assume that the y, displacement in y-axis, equal to a sine wave a sine omega t, where omega is the natural frequency of the system, which is k over m, the square root of k over m. K is the stiffness of the spring, m is the mass of the spring. So the same picture here, the vertical movement of the mass, and because of the spring, we will have it in here. So this is the spring, and this mass is moving up and down in y-axis. So sometimes you will find that the mass will reach a peak or high value in compression, and this is called A capital. And sometimes the same mass will go down to a highest value, which is the same value of A amplitude. A is the peak value, the highest point, either positive or negative. And this motion will continue forever, up and down, up and down, up and down. Each time you can reach, so you start from zero, some values, and then you reach the peak point, and then again coming to zero, change direction, highest value and then going back to 0, this is one cycle. So starting from 0 peak, 0 negative peak, and 0 again, we complete full cycle or one cycle. So this is a sinusoidal wave depending on the amplitude A and depending on the frequency omega. To relate the frequency omega to the elements of the system, it's equal to k over m under square root, where k is the stiffness of the spring, mass is m is the mass of the block or the element. We know that m is inertia or mass, k is stiffness. So what is the omega in case of this sine wave? Omega will be the frequency, the repetitions of cycles with respect to time. So how many cycles in 1 second will give us the value of omega or frequency. And of course we know that frequency is the inverse of the period t. So if you count the time needed to complete one period t, this is 1 over f in hertz, or we can change also the frequency in hertz f linear frequency to omega, the angular frequency omega over 2 pi. So for simple harmonic motion equations, if we assume that this harmonic motion, as we discussed in this figure, A amplitude sine omega t or A sine square root of k over mt. This is the value of displacement. If we differentiate that y to get y dot, which is velocity, differentiation of sine will bring us this cosine. So omega A cosine omega t. If we differentiate again, you will get the value of acceleration A, which is minus omega square A sine omega t, or exactly minus omega square and y. This is the same value of the initial original y. So we have the three elements for displacement y, velocity y dot, and acceleration y double dot. Good. If you want to see the relation between displacement, velocity, and acceleration, if we can compare this, A sine and omega A cosine and minus omega square y itself, which is sine, we can find that we have some differences. So this curve is for displacement, this wave is a displacement, and this is velocity, and this is acceleration. We can realize that the peak value or the amplitude is different. This is some A, this will be higher, and this will be even much higher because of that value. So in the y, we start with only A. In velocity, we have A multiplied by omega. In acceleration, we have omega squared multiplied by A. So the amplitude is higher in acceleration, the highest in acceleration, and lowest in displacement. Another thing is change from sine to cosine and sine again. So we have some phase shift. So if displacement starts from 0, it's a sine wave. The velocity starts from 90, which is a cosine wave, and then the acceleration is shifted 90 degrees from velocity or 180 degrees from displacement. So we have two differences, the one in terms of amplitude and the other one in terms of t, time, which is the phase shift between displacement, velocity, and acceleration. So to start our experiment, it's only a simulation. We don't have any machine running. So if we run the experiment by going to start programs, the machine health monitoring program, let me go to my desktop. This is the software for machine health monitoring. Double click. So information, run experiments. Run experiments. This is experiment number 3, vibration fundamentals. And the first element is vibration fundamentals. Good. Let me go back to the PDF. So we selected experiment number 3 and we have this panel displays. So to start, we need to examine the front panel and observe the differences in phase and amplitude between the three charts as we discussed earlier. So we can clearly see that the values of amplitude in here is higher. Sorry, this is displacement. The velocity is higher than that, and acceleration is even higher than both of them. In terms of frequency, all of them, they share the same frequency. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 waves in 1 second, that means frequency is 10. Same thing, we have the values of frequency and velocity and acceleration, because all of them, they are generating from the same wave of displacement. And we can reduce that, just play with the parameters to reduce the frequency to 3. For example, we have 3 cycles per 1 second. For amplitude, if this is 10, that means this will be omega multiplied by 10, that means 30, and this will be 300. So we know already the difference. And in terms of the phase shift, we can see that this value is going from 0 for a sine, and this is going from 90 for a cosine, and this is starting from negative wave, which is 180 phase shift from displacement. Good. For the second step, change the frequency of the system and observe how the signals change. Is there any difference? No, we know that. Already we discussed this issue. So if we change frequency to 3, for example, all 3 graphs will have the same frequency. If I change that to 6, all figures will have the same value of frequency. Good. Number 5, how could we change the frequency of the system in real life? So we know that the frequency, if we go back, frequency is square root of k over m. K is stiffness and m is mass. So if you change either the value of k or m, you will affect the value of the frequency, natural frequency of each system. So this answer will be by changing the stiffness k or mass m. Let's go back again for the questions. So to change frequency in real life, we need to change either the stiffness k or the mass m. Good. So number 6, change the amplitude of the system and observe how the signals change. Is there any difference in the amplitude between the 3 measurements? How much is the difference? So we know that by changing this amplitude, each time this is higher than this displacement, and acceleration is higher than both of them because of the omega frequency, omega a and omega square a. Good. And how could we change the amplitude of the system in real life? How to change the value of amplitude? We can change amplitude by changing the initial displacement of the mass. So if we build that mass in the beginning, if we build higher value of amplitude or initial displacement, of course this value will be higher, the first value, and then the oscillation will be based on that. So we can do this by changing the initial displacement. And another question, yes, that's it. This is the questions all related to the fundamental of vibrations. We can save our experiments by clicking save. So graphs will be automatically saved in an Excel file, but we don't need to do so. And this is the end of the first section. We can click return button to exit the experiment and return to the main window. If I return, so this is the 3 sections. We are done with the vibration fundamentals. Let's go now for the free vibration, or free and damped vibration. So in this section, the free and damped vibration, we are talking about the case of no damping. So if you remember, we have 2 forces, one of a spring and the other one of damping. In this case, we are not considering the damping effect, and we don't have any external force. So there is no force and we don't have any damping. That will make our equation of motion. Where is that equation? Yes. So summation of forces, Newton's second law, equal to ma, mass and acceleration, where acceleration is the derivative of velocity with respect to time, or the second derivative of displacement with respect to time. So this is ma, and this is summation of all forces. In our case, without damping, we have only one force generated off the spring, which is F equal kx. So putting that together, we will have negative kx equal to ma, or this is the system equation ma, which is the second derivative of x with respect to time, plus kx equal to 0, 0 because we don't have any other forces, external forces. So this will be the system equation in case of free damping, or sorry, free forces and no damping, undamped vibration. The solution of this second order ODE will be x, the displacement at any time, will be A capital, the amplitude, cosine omega n, the natural frequency, which is k over m multiplied by time, plus the phase shift, if any, and depending on the initial conditions and initial velocities. So the value of A, that amplitude, is depending on the frequency, omega n squared, depending on the initial displacement of the mass, depending on the initial velocity. So through this formula, we can find the value of A. The phase shift y is depending on omega n frequency, initial displacement, and initial velocities. So this will be the response of a free vibration undamped system. By saying undamped, we realize that the amplitude at each cycle is similar, so there is no reduction in amplitude, there is no waste of energy, this value is not reducing. Each time you will keep and maintain the same value of amplitude. Good. So for the procedures, we need to run the experiments and click the second section for vibrations fundamentals, and we select the free undamped vibration. So let me go there. This is the free undamped vibrations, and we see a simulation for a mass. This red one is a mass, and we have a spring, and we have also a damper, but in this case we're not considering the damping element because we have undamped system. As you see, free undamped vibration. So let's go back to the manual and check what do we have. Run the experiment and record the parameters that you can adjust. Of course, we can we can change the stiffness. So I can select a spring element with less stiffness or high stiffness. I can change the mass, so I can have 2 or 6 or 8 or 10. So I can change the initial displacement and the initial velocity. They are 4 values that I can control or change. We need now to consider the effect of changing the stiffness. So we will try 2 values of the stiffness. One is 10 and the other is 70, and each time we need to look at the response of the system and see how changing the stiffness is affecting the frequency, the speed, and the amplitude. So 3 of them, we can check this box for increasing or this box for decreasing, or we can comment if that change is not affecting the system. So let's go, and for the other values we can keep them at any value because we're not interested now in looking at their values or their changes. But for spring stiffness, let's do some. This is 10, and let's simulate the system. You can see that the object is moving up and down for 8 seconds, and this is the graph. So from here we can see that this is 7.5, the amplitude is plus 7.5 and negative 7.5. Let's keep this in mind, or we can take a snapshot, for example, to keep that value. If we change the spring stiffness to 70 as mentioned and run again simulate, remember that the amplitude was 7.5. If I click simulate, clearly we can see that the amplitude is reduced from 7.5 to almost 5, and also I can see that the value of frequency, the cycles in 8 seconds compared to 2, we have now 1, 2, 3, 4, 5, 6. So now I clearly understand the effect of stiffness on the frequency and amplitude, or in general on the response of the system. So you should be able to answer this. What is the effect of increasing the stiffness? Let's go now to the mass. What if I control the mass and change that from 1 to 10? What is the effect on the system? So I will keep everything, but now for mass I will select 1 and click simulate. Good. So for less mass, it's obvious that the system will be able to oscillate faster, and 1 2 3 4 5, maybe 10 values of oscillations in 8 seconds. This is for mass 1. What if we check mass 10 and simulate? Slower and less values and higher amplitude. So we can compare from these two graphs together what is the effect of changing the mass. You will be able to answer this question. What if we select the initial displacement? The initial displacement from 1 to 8 meters. This is a mistake here. So displacement from 1 meter to 8 meters. Let's go back. So I'll keep everything like a normal or average value, and for displacement I will select 1 and click simulate. I can see that it's on almost 2.5. 1 2 3 4 4 peaks. What about 10 and simulate? Different amplitude and different frequency. We are done with that. What about the velocity? Initial velocity from 1 to 8. So initial velocity, let's keep those values, the nominal values, and change the velocity from 1 and simulate 1 2 3 4 5 peaks on almost 6 or 5.7 something. If I change the velocity to 10, for example, and then click simulate, there is small difference of that value, so the peak is higher now, and the 1 2 3 4, or we can say there is small difference. There is a small difference, but cannot be in terms of frequency. We cannot look at it unless we have a specific measurements. But for the amplitude, I think we can see that this, with higher velocity, we have higher values of amplitude. Good. So we can save those results, or we can simply take a screenshot of them, and that's it. Good. For now, instead of of course we do it by the experiment, but remember that the theory support the same understanding or the same concept. So for amplitude A, it depends of frequency, or let's start even with that value of omega n, k over m. So obviously if you increase k, you are having higher frequency. If you increase mass, you will have less frequency. So all the variables that we change, you can look at them from the equation, and then you can decide what is the effect of increasing any element with respect to amplitude or frequency. Good. So this is the end of section 2, which is the undamped case vibration. Now to go to the last section or last element, this is the free, but we add the term damped vibration. So we have damping. That means the energy will be dissipated by the cause of the damper element. So you will see this decay. The peak number 1. So we have less value of amplitude and less value and less value. We have this curve, decaying curve, for displacement and time graph. In this free body diagram, we have the spring, we have the mass, and also we have the damper element C. So because of this damper, we will introduce a new force of the damping element, which is C, damping element, multiplied by the velocity. So we have two forces, Kx, the spring of the force of the spring, Cx dot, the force of the damper, and this is Ma from Newton's second law, and this will be our new equation of the system. Solving that equation, the second order ODE will give us this x, the displacement. It has two parts or two sides, one for the oscillations itself, the sine or cosine wave, and some the exponential term for decaying it's exactly this envelope of decaying, showing that the value of amplitude is reducing at a time. So same values, we can find the amplitude. It depends on the initial velocity, on the omega n frequency, on x0 the initial displacement, on zeta where zeta is the decay constant or the damping coefficient, and omega d the damping frequency. It is a factor 1 minus 0 square multiplied by the natural frequency. So we can find the amplitude A and the phase shift y, and we can plug them in here to find the response at any time. So to find the displacement, you plug y and time and all parameters to find the value of x. For experiment, the same thing. If we open the software, we can go to the third section, free damped vibration. It's basically the same screen, but let's go back, return. This is section 3.3, free damped vibration, and click this. Aside with the three values, we will have the damping ratio element in here to control the zeta or the damping element. So we need to run the experiment, adjust the parameter of the system. How do they affect the behavior of the model? There is no need to repeat the four elements 1, 2, 3, 4 because we already did in section 2.2, in section 3.2, sorry. But the damping element, this is new. So if we change, okay, this is 0.1 and simulate, this is low value of zeta, you'll see that the motion is dying, starting from 4 and then 2 and then 1 and then 0, and this is the effect of damping or reduction of the motion or oscillations. If we have 0.8, you'll see that higher values of damping, it will cause the motion to die faster in here, and there is no oscillations. If we select, for example, something average 0.5 and simulate, we will have something in between, some oscillations. So this is basically the damping coefficient zeta. Good. If we set the damping ratio to 0.2, observe how the signal decays and doesn't oscillate forever in the previous experiment. Good. So, sorry, if I say select 0.2 as mentioned, you will see that we have one peak, 2 and 3. 3 cycles or 4 cycles, and then the motion dies. At what ratio does it vanish completely? So this oscillation is going up and down, up and down, up and down, up and down. If I increase that to 0.4, one up and down, up, only 3. If I increase that to 0.6, it's only up and something. If I increase that to maybe 1, we cannot simulate the case of 1, but 0.9. So we understand that anything less than 1 is called underdamped, and we will have oscillations up and down. In case of 1, this is critically damped. There is no oscillations. In case of more than 1, this is overdamped. Good. So this is the end of this section. Basically, we studied the effect of the damping element zeta, and we experienced the case of low value of zeta or higher value of zeta. So we are done now with our experiment, and we can return and close the software. And thank you very much.